outright sentence.
All right, good morning, everybody. I could read the emotional state of the room yesterday after you were done with your exams, and it wasn't good. I just got that sense from you, right, that it was rough when there was more than half of the class still there when I called time, right? I'll find out starting today whether or not that's true. A couple reminders. Let me go back, some statistics. And this is from memory, so forgive me if I'm slightly wrong. I'll use numbers, but these are ranges. It's the normal average on this exam ranges between a low 50 and a high 40% raw score, which is why we have an exam autopsy, to try to recover some of that, okay? I want to be very clear. I'm not saying that you are going to get that score. I'm just saying the raw score, the right, wrong, right, a question right, question wrong, not looking at anything you put down on the page, right, generally hovers in that range for this exam. The right, wrong score for the second exam is somewhere like in the mid-70s usually, just the raw, and then it kind of moves up from there as I go through and grade. So, and that's been uniform over my career in the classes I teach. That's typical when I talk to other teachers, both here and at other schools. It's kind of what I experienced. I'd love to think it's because of a systemic failure in our teaching or whatever. I've worked my entire career to not teach the way that normal physics teachers teach. And I can tell you that this stuff is just hard. It's just hard. Did I make the exam too hard? Maybe. I was worried when I saw lots of people still there, right? Okay. So maybe I did something, I got to figure it out, right? Between now and Tuesday, I caution you against doing anything rash. There's bridges and high places. There's a lot of people missing today, okay? And you're here, so that's the first half of the battle, okay? If you are listening on YouTube and you decided not to come today because you're like, oh, nothing important happens the day after exam, you are wrong. You're wrong. And you need to catch up. So you're in the right place because we are going to move forward and we're going to go fast, right? Like was mentioned, it's like you got no time for the breakup, right? We're going right back into the next relationship. So hang on for the ride, okay? If you're not here today, if you're listening on YouTube, you're not here today because you feel like a failure, you need to drop, don't do that. Come talk to me first, okay? If you feel like you got to drop anyway, come talk to me first. That might be what has to happen. I'm not saying that isn't going to happen, right? But what I'm saying is let's figure out all your options before you go do something, right, rash. The other caution I have is you guys are your own worst graders. Over and over again, okay? Students go, and then they look at their score and go, oh, how did I do that? So talk with each other. Emotionally support each other, but I caution you about running away with, oh, I didn't do any of that on the exam, I must be a failure, okay? So we'll see what comes out in the wash. I guess you guys will be able to tell on Monday, right, what mood I'm in, okay, after I've looked at your exams. But yeah, this stuff is hard. This stuff is really hard. And the test autopsy is a way for us to correct. Figure out what's going on. And did I read the room right? Did you guys walk out pretty upset? Yeah. That was the general feeling I got, right? So, and some of you were like, I didn't feel upset, now you're all worried. It's terrible. I should just grade the exams and give them back to you right away. But that would be even worse, because then it would be really bad. All right, moving forward. When's chapter 24 homework due? It's not this Monday, right? Right? It's not this Monday because it's going to take today and Monday to get through it, which you're like, yes, a week off of physics. Here's the truth. I know that 65% of you have not even started the homework on the Saturday before the Monday that it's due. How do I know that? I can see, right? I can see who started. I can see who's not, right? There aren't very many of you in GRASP. Like a shockingly low amount compared to other semesters. And I know there's various reasons for that because it's work and all that kind of stuff. But I half suspect that I could correlate performance on this exam with the amount of time you spent on doing your homework. Like from the time you started it, like first access just to look at it till when it was due, right? So you can't do that. 2 days is not enough to get this material. So if that's you, if you're one of my 65%, you're like, yes, I'm in the majority. It's not a good majority, okay? Today, open the chapter 24 homework. Look at all the problems. Start digging in. But Mr. Balogh, I've got an organic chemistry test today. I got a paper due. ChatGPT can do the paper. Take some time every day to do physics. It doesn't have to be 2 hours a day. You can have a day or 4 out of the week where you really dig into physics. But every day, let your brain concentrate on this stuff a little bit. Okay? Don't be afraid of that brick wall you run into in the problems. Those are good brick walls. Keep plugging away at it. If you're starting your homework 2 days before the day it's due, it's kind of like you've scouted out the marathon course, like you know where to run, but the entire time you've been doing it on a motorcycle. And now the day is time to run, and what's going to happen? You're fat. You're not in shape, right? Your body's not ready for it, okay? So, and then you fall at the midway or not mark. So yeah, I beg you, right? I've been noticing this, and I bring it up now because there's still time to correct. There's still time to fix it. And I want to help. I want to help you fix it. So if you're at a loss as to how to fix it, reach out to me, email, whatever. We can meet on Zoom. Let's figure it out. I happen to know a professional in these cases. All right. So with all that being said, kind of a downer to begin class with, right? Okay. We need to simplify. We need to move in a direction away from all this complexity. And let's face it, one of the reasons that this stuff has been so hard in this first unit has to do with the V word. What's the V word? Vectors. Vector directions of things. I mean, let alone setting up an integral and this weird idea of a field and charges and all this stuff, Mr. Balogh. You just throw on that. So let's get rid of vectors. Should we have a vote? Get rid of vectors, yes or no? The answer should always be yes, right? Like if we can get rid of vectors, then life is good. Now, is the electric field a vector? Yes. So can we just ignore electric field? No. Is force a vector? Yes. Can we just, I don't know, ignore it? No. But in physics 4a, we had a method for dealing with forces and velocities, all these vector type things that took away their vector nature. and let us just run with it and do some actually pretty complicated things. Instead of just having to do like inclined planes where everything was just smooth and nice, we could now do roller coasters and loop-de-loops. We could throw the ball in the presence of air friction and still figure it out. Do you know what I'm talking about? The words on the screen right now. What is the thing that took the vectors away and let us run with it? Did kinematics, you did Newton's laws, and then we did, or you did, energy. Energy, conservation of energy. Whether you hated it or loved it, it didn't have vector. Does the kinetic energy have a vector? No, it's just kinetic energy. What about the potential energy? No. None of these were vector things. And so energy is a way to deal with some of these systems so that we don't necessarily have to be too worried about their vector nature, but we can still predict and we can still do things. That's where we're going today. We're going to try to strip off this extra baggage of vectors and charge forward and develop a conceptual framework where we can think about things in terms of energy. And then we will morph that into a discussion of how electrical energy and power works and develop real-world circuits that run our lives today, from our cell phones to our microwaves to everything that's got electricity flowing through it. So this is where we begin, right? And we're going to start with potential energy. So just a quick review of potential energy, right? If I hold the ball here, does it have potential energy? Why? Because gravity wants to pull it down. Now, it was a bit of a trick question because I could be holding it here and it could have zero potential energy. Because I'm free to choose zero wherever I want, right? I could set zero to be here, in which case this thing has zero potential energy at this point, right? But that doesn't change the fact that if I let go, the gravitational field is going to do work on it. Back in 4A, you talked about gravitational force, but is there a pattern of forces here because of the mass of the Earth? Yes, and we know what that pattern of forces is going to do. And so we tended to say that zero was down low, and if I put it up here, then it has positive potential energy, right? And so I could take that positive potential energy, and if I let go of it, where's that potential energy going to go? Into what kind of energy? Kinetic energy, right? We swap forms of energy around, okay? If I put zero at the tabletop, and the ball's on the tabletop, how much potential energy does it have? Zero. If it's below the tabletop, what sign is the potential energy? Negative. And if it's above? Positive. It seems kind of arbitrary, like this choice of zero. I can kind of put it wherever I want, and everything will change. That's true. But the change in potential energy is always the same. Regardless of where you put zero, the delta, a comparison between initial and final, will always stay the same. And I'm not going to go into the proof of that. You have to either remember from Physics 4A or trust me. But it's deltas that stay consistent regardless of where we pick our zeros and directions or anything else. All right. So what does that have to do with electric potential energy? So we taught you about mechanical potential energy in Physics 4A. That was gravity. It was elastic potential energy where springs were involved or bungee cords or rubber bands or something like that, right? It was always this idea that we were storing something, right? In a spring, it was the storing of energy and the stretch of the spring and the spring wanting to come back to its equilibrium. In gravity, it's the storing in a gravitational field, right? And having the potential to change where it is in that field. So when it comes to electric potential energy, hopefully it's not that big of a stretch, right? To realize that we're going to be storing energy where? Like what field? The electric field, the one we've been dealing with the entire time, right? So how do we go about doing that? The there's a close tie between work and energy. And just sort of as a simple, I'm not going to worry too much about dot products and stuff yet. Work is the amount of force that's applied to something times the distance that force is applied. Okay? It comes out in units of joules. And then when it comes to energy conservation, we have this fact that the initial energy and the final energy have to be equal to each other. But we could introduce extra energy into a system by doing work. A rocket provides additional work from its thrusters, right, from its engines, that's not accounted for by gravitational potential energy. So when it came to, I don't know, dropping a ball, right, we tended to talk of this as a high potential energy, and this is a low potential energy. And the work here was the force of gravity, which is mg. And the distance we dropped it was h. It drops through a height. Did you guys use mgy or mgh? You remember? mgy? We'll use your language. That's fine. mgy. All right. So we said, well, this is work. It's force times distance. And then we kind of just said, well, let's redefine this and call that the potential energy, right? The gravitational potential energy was m times g times y. And then we went and did a bunch of problems. Okay, so electrically, what does this look like? Let's take a conductor, like a plate, okay? And let's just put some positive charge on it. And then I'm going to take another plate nearby and put some negative charge on it. We know something about the electric field that is going to be produced in that situation. Where's the electric field going to start? It's going to start on the positive and end on the negative, right? So we're going to have electric field lines that are just going across like this. I'll try to be neat. Why not? All right. So let's drop a positive charge, a little q right there. Okay? So I've got this electric field. I've got this charge in the electric field. And if I handed you my stylus and my iPad and said, draw the force on that charge, which way would you draw it? Any ideas? To the right? Why would you draw it to the right? Because we know that the force on a charge is equal to that amount of charge times the electric field that it's in. That comes from the electric field definition, right? We said electric field is the force divided by a test charge, right? So you rearrange that and you get the force is equal to the charge times the electric field. All right. So we know that, and since force and electric field are all vectors, and I thought you said, Mr. Bailey, we weren't talking about vectors. We'll stop talking about them, don't worry. We know that the force would be like this, right? So make the analogy here, right? Notice that the ball gets pulled down from high gravitational potential energy to low gravitational potential energy. I deliberately drew this one sideways, right and left, right? Where is the high potential energy? It's where the positive charge is. And where's the low electric potential energy? We're in there. How do you know that? We know where it's going to go, right? If we let go of this charge, which way is it going to fall? Air quotes. It's going to fall towards lower potential energy, right? So we could come in here and say, okay, well, this side must be the low potential energy, and this stuff must be the high, can't spell, potential energy and low potential energy. All right, but what is it? Like, okay, kind of get that idea, right? The positive charge is going to fall, right? And the electric is going to follow the electric field. What is it? Well, again, we know that work is equal to force times distance. The force is what? It's the charge times the electric field. That's the force. And then There's going to be some distance. I think your book uses delta S. I'll use X right now since we're just working in the horizontal. Realize that S is a generic thing. Technically it should be R, but that's all right. But we've got a force times a distance here, right? We know the work is the force times the distance. And just like over here with potential energy, we say, okay, well, we know the work. Why don't we just define that work, that idea, right? Because we'll put work into getting it there, and if we let go, that amount of energy is going to come out of it. We're going to define this statement right here, this charge times the electric field times a distance, as our electric potential energy. Q times the strength of the electric field times the distance that that charge moves in the electric field is our electric potential energy. In a very simplified linear form. We'll break it out into a general form here in a second, where integrals will come back. But let's stop and make sure conceptually we are oriented here, right? Which way is downhill in this diagram? To the right. It's to the right, okay, from the positive to the negative. And unfortunately, this is where our analogy with gravity breaks. What happens if I drop a negative charge in there instead? The negative charge is going to fall which way? Uphill. I'm sorry. I'm not responsible for how the universe is built. Okay? You got to take that. It's way above my pay grade. Okay, right? But what I can point out is that as far as gravity is concerned, there's really only one way that's downhill. But for electricity, downhill depends on the sign on your charge. For positive charges like to go from positive to negative, right? Okay. But what do negative charges like to do? Roll uphill. Negative charges roll uphill.
Does that mean the high potential energy and the low potential energy switch, like for the charges?
Apple, why did you ask that question? It's a good question. Everybody hear the question? Does that mean that the definitions for high and low potential switch? No. By choice. In other words, we as human beings, as we've cooked up this way of understanding how the universe has worked, right? We decided that those words, high and low potential energy, are always with respect to a positive charge. Okay? And that negative charges go in reverse.
And that's why the analogy stops.
Right. And that's why the analogy breaks down because there's no negative mass. Okay? So by choice, it's not like Ben Franklin sat down and said, I'm going to screw up the lives of students 200 years in the future. By choice and just by fiat or by the fact that we were building the car as it was rolling down the road when it comes to all of our science, right? We inherited these choices, like the sign on the electron, and the fact that high potential energy is defined as what would a positive charge experience. Okay? So it's a can of worms, but we choose not to open it and stick with how it's always been done. Okay, so what are the units of potential energy? Joules. Right? Right? It's an energy, right? So it's going to turn out in units of joules. Wait, a kilogram times a meter per second squared times a meter, mgy, right? A newton times a meter is a joule? Well, yeah, that's what we told you back in Physics 4a, right? A coulomb times a Newton per Coulomb times a distance is what? It's a Newton times a meter, which is, by definition, a joule. Okay. I do want to point something out. Work, and this just kind of comes back to haunt us all the time. When you do work, it's always equal to the negative of the change in potential energy. If you increase the potential energy of an object, then the work that gravity did, positive or negative? If I pick the ball up off the floor, which way did it move? Up. Which way was the force of gravity? Down. What kind of work is that? Negative. We change it, the delta for the energy was positive. We brought it from 0 to a higher value, right? But the work that the field did was negative. And this was something that may or may not have haunted you back in 4A. And maybe is only starting to haunt you now. It's going to haunt you. So if I change the electric potential energy, is it opposite the work that the field does? Yes. Okay. In general, this is where we'll pull out some integrals. Changes in potential energy. U, by the way, is the accepted symbol for potential energy, and I use it quite a bit. I think your book starts using it now. They didn't use it back in some parts. They used it in 4A. Did Dr. Kerfoot ever whip it out?
Yeah.
Okay, good. Good for him. That's the way it should be. Is equal to differences in work. And if your force vectors and your path vectors as you work through these fields are different, then you do have to integrate that force along its path in order for this to work out. Okay? So that's the generic form. And we again know what this force is. It's Q times E. And there are vectors in it, but it's a dot product. And a dot product always returns a scalar. Okay? And we are going to call this the change in electric potential energy. While we are going to integrate this chapter, you are not looking at the integral you're going to be doing. So why even bring it up? Integrals, right, allow us to capture this idea that we're going to add up a bunch of little things together. And what we're adding up, so like, for example, if my path through this field were something like this, what this integral tells us is it doesn't matter what the perpendicular parts of this motion are. Because if your direction that you're going is perpendicular to your field, what's the dot product? It's 0, right? What's the only part of the motion that matters? How much of it is in the same direction as the field. So what ends up happening is that the integral picks off this distance right here. I mean, technically, like that horizontal distance right there, okay? But it picks that off, right? And kind of handles it for us. What we do instead of having to do those integrals is we kind of cheat and go, well, you know what? We'll make sure this always works out. So we'll just call our change in gravitational potential energy, it's going to be negative E times S. Or oftentimes you'll see it written as delta S. Is that gray too faint? That right there is kind of a shortcut. Where delta S isn't the actual length of the path that the particle took through the field. It's the length compared to the electric field itself. It's a little bit easier to deal with. Okay, so what have we talked about? We brought back something from physics 4A, the concept of energy. And are we going to conserve this energy? you betcha. We'll get there, okay? But I wanted to make sure that we remembered things like the relationship between work and energy, because we're going to want these charges to do work for us. The lights are on right now because charges are doing work. They've been given energy, and then that energy is converted into photons somehow, right? And by conservation of energy, we can't get more out than we put in, and so on and so forth. We want to be able to talk about these processes. So this is the very, very beginning of being able to talk about that. But now I do have to introduce you to something that is new, that we didn't talk about in Physics 4a and is absolutely unique, it's kind of a lie, to electricity. And that's the concept of the electric potential. What word is missing? But Mr. Balogh, you just finished talking about energy. I know I did, okay? But this chapter isn't about the energy. It's about the electric potential. And this is a very, very unfortunate name. You see why, okay? So we're going to correct it. The electric potential is defined as the change in electric potential energy divided by charge. Okay. We've been here before. Do you remember Coulomb's law? Yeah, unfortunately, yes, Mr. Balogh. You tortured it with me. You tortured me yesterday with it, right? Coulomb's law was pretty bad. And then we got to electric field. And in the definition of electric field, we took Coulomb's law and kind of stepped in a direction of simplification in the sense that there was like one less charge to keep track of, right? Had this test charge, and fields were a little bit easier to set up than Coulomb's law and that kind of stuff. And I know you guys are looking at me going, that's not true, Mr. Balogh, just look at my test, right? We're trying to do the same thing here. Okay? Because it turns out that measuring electrical potential energy directly is challenging. But measuring electric potential, where I don't need to know like the charge I'm using to sample this, is really nice. The analogy to gravity is I don't have to worry about the mass of my tennis ball. I'm trying to pick off a value where it doesn't matter if I put a tennis ball or an elephant, okay, in that position. I'm going to get some information about what's going on, sort of independent of that mass. And as a matter of fact, in mechanics, there is an analogy to this, but we don't ever teach it to you in 4A or 4B or 4C, okay? This is your first time where we're trying to divorce sort of a fundamental idea like mass and charge out of a concept. And we're going to use that concept not only because it actually is easier to deal with, but because it's something we can actually measure in the real world. Electric potential energy is near impossible to measure directly. Like we don't have a meter that can go measure it. But electric potential, we measure all the time, and you'll see why right now. The symbol for electric potential is V. Capital V. Technically, we should have a delta on the front of that because we're changing in energy, which means we're changing an electric potential. And I chose the symbol V for a very specific reason. What's the other name for electric potential? It's voltage. And now, how many of you have heard of voltage? Yeah. Where do you run into voltage? Where, like in your everyday life, where have you run into voltage? In your pocket? Yeah, your phone needs how many volts to charge? 5 is the answer. Okay? The answer is always 5 for the voltage. The number that they throw around for quick charging is either the power in watts or the current in amps. We'll get there. We'll get there. But all USB, which is where all of our devices get their power from, the universal serial bus, use 5 volts of electric potential. Now, is that energy? No, it's voltage. What's voltage? It's a change in electric potential energy divided by the amount of charge that was used. You're like, okay, so what, Mr. Okay, so what's the voltage on like a AA battery? 1.5. Okay, and so usually you have to stick 2 at a minimum, say into a flashlight or something like that. Okay, what's a flashlight, Mr. Balogh? There used to be an old thing that was separate from your phone that lit up the darkness. You put 2 of them in, which means that that device is running on how many volts? 3 volts. But your calculator needs 4 batteries, doesn't it? So what's your calculator running on? 6. Okay. Most devices run on a multiple of 3, it turns out. The universal serial bus kind of broke that and did a multiple of 5, which was a good thing, right? So voltage is very much something that you've run across, but have never really understood, like kind of what it is, why it is, how it works, where it comes from. And that's what this whole chapter is about. Okay, so again, just to be, I don't know, careful and get everything in there. Do you notice how my change in potential energy has that charge sitting in that integral? The voltage in its big form, okay, is going to be an integral of the electric field times a path times dot product right there, okay? We will come back to this integral of finding the connection between electric field and electric potential later at the end of this chapter, maybe on Monday. Okay, we are going to stick primarily over here to the more simple delta energy divided by the charge, and then kind of use this to keep running. Okay, so what's like the best thing on the screen right now in terms of the electric potential? You just read what was on the screen, but like, what's the best feature? The feature that we set out this morning to get rid of? There's no vectors, right? I mean, there's one hiding in that dot product right there, okay? But eventually we just come out with a scalar. So what is the power, right, of working with the electric potential? Let's dive into that, but before we do, what are the units of the voltage? Volts, right? That's why we call it the voltage. So like, even though it's called the electric potential, right? We kind of like go, voltage. And it's called the voltage because it has units of volts. What's a volt? It looks like it's a joule per coulomb, right? An energy divided by a charge. But it also looks like it has what are the units of electric field? It's a Newton per coulomb. And then we multiply by a distance. Meters. What's a Newton times a meter? It's a joule. So we're still consistent here, right? But this means that we can, since this is E times a delta S equals a volt, the electric field has another way of being expressed. What are the units of the electric field? A Newton per coulomb, which is identical to a volt per meter. I screwed up a couple times when people would come and ask me questions like in GRASP or something, and I'd start looking at the units, and I would say, oh, well, the electric field has units of volts per meter, you don't have to worry about it. And people would look at me and go, no, it's newtons per coulomb. Oh, that's right, it is newtons per, for you. Right? But for everybody else, it's volts per meter. I would caution you against going down the rabbit hole of units. The safe place to be is always use standard metric units. Use standard metric units, you're going to get standard metric units out. But now, your answer for electric field can be either newtons per coulomb or volts per meter. Those are identical units, but very different conceptual frameworks, isn't it? And it turns out the volt per meter one, super useful. Like super useful for figuring out the electric field in a thundercloud, right? There's no electric fieldometer. I can't take two probes and just measure the electric field. I can't fly my drone into a thundercloud, figure out what's going on in there with an electric fieldometer on it. But I can put a voltmeter on it. A digital multimeter, a volt. What does a voltmeter measure? Volts. If I measure the voltage over a distance, can I figure out what the electric field is? And why would I want to know the electric field in a thundercloud? Do I want lightning to strike trees anywhere near Fresno when we've had all of this high temperature and the water amount in the bush is low? Would I want to be able to maybe find a way to direct the lightning somewhere else to prevent forest fires because humans are stupid and do climate change? Maybe. So, yeah, rubber's starting to hit the road. Okay. You remember our charge plates? Where is the high voltage? On the positive side? Why is it on the positive side? Because that's where the high potential energy was, right? Voltage is not energy. And so why is the term electric potential so unfortunate? Because it sounds exactly like electric potential energy, doesn't it? How do you know which one you're working in? Look at the units. If it's voltage, it's electric potential. If it's energy, it's going to be in joules, right? But that doesn't change the fact that we can borrow that same concept and idea and call this side the high voltage side, the high potential side, and this side the low potential side, or the low voltage side. Potential and voltage are words that are constantly used to mean exactly the same thing. Named after Alessandro Volta, who came up with one of the first batteries. All right, so let's notice in these diagrams, I have depicted electric field in two different diagrams here, right? Just split the screen down the middle. The electric field that I've drawn right there is pretty much the electric field that we saw between the plates, isn't it? So which side of this field is the high potential side? It's got to be over here, right? And this one's the low. Okay, take a look at that diagram over there. Now, notice that the electric field vectors point towards what? Well, in that picture, they point to the center. But in general, electric field lines point towards what? The high or low voltage? Hi Siri. They go towards the low side, right? They point in the direction that is downhill, as long as we're thinking about positive charges, right? Okay. So, where is the high potential in this picture over here? It's all around. Everywhere around this thing is high potential. And where is the low potential? It's in the center. And where is a positive charge going to go if I drop it anywhere? It's going to go towards the center. It's going to flow towards that zone of low potential. If it's a negative charge, which way is it going to go? The opposite way. You think about the charge, oh, it wants to roll towards the low, but it's negative, which means it's going to go the other way. And why are electrons annoying? Because they're negative. And that is Ben Franklin's fault. All right, let's do a quiz. Here we go. All right. I want to teach you about a dead art, a dead skill, a skill that has gone the way of the dinosaur. And why am I doing this? Because I'm an old man and I want to teach you old ways. No. Because the analogy is an important one for being able to visualize and understand what's going on here. The old skill that I want to teach you is how to read a map. And the map that I want to teach you how to read initially is going to be an actual map about actual physical location. But we're going to make a map of electric potential. And this map is going to give us powerful ways to sort of interpret what's going on and what's going to happen. What is that? Oh, that's a map. Oh, what kind of map is it? A topographic map. Okay. Before the days that we could carry all of the world's knowledge in our pockets, we carried around paper maps. And a special kind of paper map was one that would indicate to us changes in elevation. Now maps, pieces of paper, they're inherently two-dimensional, aren't they? But you can get a three-dimensional idea by looking at a two-dimensional representation. And in this map, there's a map of Yosemite Valley, okay? And there's special lines on this map that to the person who's trained to read it will indicate what's going on as we look at the map. So let's look at, I don't know, like if you compare like this part of the map right here, okay, to say this part of the map right there, what has more going on? Top or bottom? Yeah, right? Those brown lines mean something. And when the brown lines are spread out, what does the terrain look like? It's kind of flat, right? There's some hills there, right? Okay. But when the brown lines are all jumbled up next to each other, what the heck is going on? It's steep. It's really steep. Every single one of these brown lines, like this one right here, okay, as I follow it around, okay, is a line of equal elevation on this map. In other words, okay, so just to be clear, you're not going to go out to McGurk Meadow and see a brown painted line, okay, on the ground, right, okay? But when I get to the meadow, I can be pretty certain that if I walk into the meadow, is my elevation going to go up or down? No, there's not a whole lot of lines down there, right? Okay, there's going to be a little bit, but not a lot. But when the lines of equal elevation start getting closer and closer, every one of those representing a 200-foot, it's not on here, 200-foot elevation change from line to line, right? Then I know when lines get close together that the terrain is very steep. If I'm walking on the edge of the valley rim right there, right? I'm on that very steep part, climbing as it were, right? If I move sideways across the cliff face. Is my gravitational potential energy changing at all? No, right? Okay. I can move along a line of equal elevation and my gravitational potential. The only way I can change my gravitational potential energy is to do what? I can climb up or rappel down, right? And then I will change my gravitational potential energy. On this map, I can tell you it's going to be a hard walk leaving from Yosemite Valley to go up to Glacier Point, because I have to cross a whole lot of these lines of equal elevation that are squished next to each other. But the walk from Glacier Point down here to McGurk Meadow and Badger Pass is going to, there'll be some elevation change, but it's not going to be as extreme, right? So nowadays we pull out our map apps, Google Earth, whatever. Nobody uses Google Earth anymore, right? Okay? And you can see sort of in 3 dimensions what this terrain looks like. And this is kind of a bad represent. So what I did here is I tried to overlay the 3-dimensional topographic data in Google Earth with the topographical map from the United States Geological Survey. And you get a little bit of a so it's like we're looking at it sort of isometrically rather than flat down like this. You kind of tilt it and we start to see some of the features, the terrain features there. We can go into our map apps and just spin it around and all that kind of stuff and ask our GPS to tell us which way to go. We live in a great age, okay? Because if you're lost in the forest now, well, it's on you. Because like your device knows where it is all the time, okay? Even when there's no cell service, it's got a pretty good idea. So why am I telling you about this? The map of electric potential follows these same rules. Just like the brown lines on this map represent lines of equal elevation, we can draw a map of equal electric potential. There is a color of line on my topographic map right here that always points perpendicular to the brown lines. So the reddish are the brown ones, reddish brown, okay? But there's another color that no matter where I look seems to always, if it's going to cross one of these lines of equal elevation, always seems to be perpendicular to it. What direction is perpendicular to lines of equal elevation? Up or downhill, right? Which way does water go? Downhill. The blue lines on here always run perpendicular to the lines of equal elevation. When we start thinking about and drawing and constructing maps of electric potential, what way is the electric field going to go? Perpendicular to the lines of equal potential. And it's quite often easier to draw the equipotential lines and then figure out what the electric field is than to do it the other way around. So again, potential we can measure directly with a device. Electric field we can't. So let's extend this analogy. Let me play a video for you and see if we can't get some more like animation and 3D-ness in here. Why did it do this? There's the answer to the next quiz. All right. Where did it go? Right there.
By the same token, the contours on this map give a clear representation of an electric field.
So those are lines
These
of
are
equal
contours
potential.
of constant electric potential.
I just said that.
And they too represent a terrain that has its ups and downs. When real ground goes up and down, the prudent traveler wants to know about it, because going uphill can be hard work. And exactly the same is true for electric potential.
Positively charged head. It's red.
Moving up the incline of potential is hard work. And the steeper it is, the harder it is to climb. Of course, if the potential isn't changing, it takes no work at all. And if the potential decreases, the field is downhill all the way. In this analogy, electric potential is elevation, and electric field is the downward slope.
Or the direction water would flow, right? If it were dumped on the top of the hill. Okay, so did you notice what happened at the top? Flat part? What did the narrator say about the amount of work there? There was no work. If you're out in the wilderness and you're walking along a trail and the trail is following the path, the line where you're not changing your elevation, is gravity doing any work on you? Are you doing any work against gravity? No. The only way to work against gravity when you're hiking out in the woods is to do what? Go up or down, right? That's when you're going to work against gravity. Not the biological work and the spending of calories and chemistry, right, and all that kind of stuff. We're talking about the mechanical work that's done, right? To do work, we have to follow the terrain. If we're moving along a line of equal potential, then no work, electrically speaking, is being done.
Because it takes no work to move a charge along a curve of constant potential. There's no component of field in that direction. So the field is perpendicular to each equipotential at every point. And that's how it assumes its familiar shape.
Okay, they've cheated just a little bit here. They're trying to reinforce this idea that positive charge is like being high up on a mountain, right? And then negative charge is like what? It's like being down in a well or a hole or at the bottom of a valley or something like that, right? And the electric field is going to do what? It's going to start where? High potential and go to low potential, right? It doesn't really look like that. It's three-dimensional, right? They're just trying to reinforce this concept and idea of an elevation, right? That this map shows us an elevation. Let's see how well you're doing with the concept of this map by doing another quiz. I already did that one. I know, so many. So many. Another 2-point quiz. Numbers 3 and 4. Yeah. Yeah. Are we running out? I think you guys should have like 1.5 left or something like that. You got 2 left? You're welcome. Anybody else need them? Well, there I go. You guys are dangerous. All right. Picture time. Let me turn down the light. I did that wrong. I should have kept the lights down. Maybe that helps you see it better. So these yellow ones are negative charges. That blue one over there is positive charge. And then there's labeled points, A, B, C, D, and E. Give you 20 seconds. All right, turn to your neighbors. Decide which of those points is at the highest electric potential energy. All right. Where is the mountain peak in this picture? It's where the positive Q, in this case the blue color, right? That would be the top of a mountain. What are the yellow spaces? They're like wells or valleys. They're the low points, right? They're the downhills, right? Okay. So now they're asking for where is the greatest electric potential energy, right? So we know that the top of a mountain is high electric potential, and at the bottom of a well would be low electric potential. So which of these points is at the highest? E? The problem is it says an electron. Where would an electron have the greatest potential energy? Now, is the potential low over here at B and D? Yes. Is the potential high at E? Yes. But now we're asking about electric potential energy. And if the question said, where's the electric potential energy high, and didn't specify the charge, you would assume a positive charge, and then the answer would be E. But because it's an electron, what do electrons want to do? They want to roll uphill, right? So they will go from low potential to high potential, which means an electron's electric potential energy is highest where the potential is lowest. And where's the lowest potential between B and D? Looks like D. D's line is closer to that, is lower down, right? as we count them. So the answer here was D. And it was D because it specified an electron, right? So give yourself half credit if you recognize that the blue was a high mountain and the yellows were down low or high potential, low potential. But then watch out for those tricky electrons. They're sneaky, right, with their negative signs. And they can kind of flip the picture on its head when we start talking about the energy that that electron has. Yes?
Where is the electron going then if it's at D? Is it going to negative Q?
It's going to go to positive Q. Okay. It's going to go to E. All right. You have enough information to be able to do at least the conceptual questions on the homework. Don't just get them green. Understand why they are the way that they are. On Monday, we are going to dive deep into the mathematics of this, and integrals will be back. We'll be integrating over disks and rods and that sort of stuff. And then we'll do the exam autopsy on Tuesday. Have a great rest of the day. Yeah. No. I'm pretty sure the homework is due